was gonna say, you haven't seen the talk, but you know all about this. Okay, all right, yeah. Great, all right, so talking about the search for Axion and dark matter specifically with ADMX, it's located here at UW over the other side of campus. So that's SIMPA. Those of you in the audience can do a tour of SIMPA. I don't know, not next week. Next week's LIGO tour, right? So it's gonna be a week. Should be. You don't get to eat out here, but there's like grass. There's an outside. Right. Now my slides don't advance at all. Give me a moment. See if I can get the right thing. I have this up. Do my slides advance? Uh-oh, I think it's having. Oh, wait. How's that look? There, okay, great. All right, so here's my dark matter story. I can keep it informal, ask about it. So have you heard about all of these dark matter things? So cosmic microwave background, individual galaxies, and then somewhere in between, galaxy clusters. You heard about all of those? You know what's going on?
I feel like I understand the galaxy examples, but what is could you talk about the first one?
The cosmic microwave background?
Yeah.
Oh, this is super interesting and super complicated. If you get someone good, they tell it to you, it sounds simple and it's not. But the idea is that, so if you go back in time, the universe is denser and hotter. And if you go back far enough, that you find that the temperature is such that electrons should not stick to protons. Like hydrogen does not exist as an atom. There's like protons and so electrons, and individually, like the energy, the KT energy is greater than the binding energy. And so it's a plasma, and then just everything's a plasma. And the deal is hydrogen is more or less transparent to light. But plasma is more or less opaque because it's a bunch of free charges and light spin of electromagnetic waves, and electric fields want to scatter off stuff. So at the period where the universe goes from being a plasma to being a bunch of hydrogen is it suddenly goes from being this thing where photons are kind of bound with matter, like bouncing around, scattering over short scales, to it being transparent. And so as soon as it becomes transparent, the photons just go on forever until they hit us. And so the photons from the cosmic microwave background is the early plasma, 10 billion years ago, the last time that photon scattered. And so what people do is they look all over the sky, because this comes from all over the sky, it's any direction, you look far enough and you see back in time, and you look at the distribution of energies of the light. And it's not a very broad distribution because it was a thermal plasma. And so nowadays it's like 2 Kelvin-ish. But there's small deviations, and deviations are kind of interesting because it tells you about what the kinematics was of the early universe plasma. And ideally, matter, that is to say non-relativistic stuff, if you just lay it out in the universe, then it starts sucking together via gravity. Places where it's a little bit overdense want to become more overdense, and places where it's sparse become more sparse because it's getting sucked somewhere else. Relativistic stuff does not care. Well, I mean, it's affected by gravity, but it's moving fast enough that it's not like matter. And so if you take a whole bunch of plasma and try and squeeze it, and there's photons stuck in it, the photons are pushing out, and the matter is pushing in, and then you've got this like balancing forces, and you write it out. And of course, it's a simple harmonic oscillator, because everything is a simple harmonic oscillator. And so you get these like overdense regions of plasma going boing, 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 boing. And so if you go and say, okay, you do get your timeline right, then you expect to see certain scales, really big scales, maybe you've only had time to collapse, get to their first part of their, it takes them a long time to squeeze together, and maybe between when things were worse than plasma and when the surface of glass scattering happened, there's only time for it to go down once. And so and this is the hard part, right? This is where the part they leave out that's really nasty, is because you're thinking, okay, so it's hotter when it's squeezed. That sort of makes sense. But then at the same time, if the stuff is moving away from you, then it's redshifted, and so it looks colder. And if it's moving towards you, it's blue shifted. And so there's that's where it gets nasty, is that you actually have to do the full physics and figure out how to map these temperature fluctuations to where something is when it's collapsing and expanding. So that's how you get that. And then if you find that it doesn't match just electrons, protons, and photons, you find that at smaller scales, that things that have had more time, or they're oscillate faster, and so they have more time to collapse, there is a component of non-relativistic matter that is collapsing and does not interact with light. So the electrons and protons and light go boinga, 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 and there's something else out there. You can imagine a bunch of neutrons or something that just keep going in because they don't see the pressure of the light. And so that's the evidence here. Now neutrons wouldn't work because they don't last very long. So we're talking about like, I don't know, many years compared to the 15-minute neutron lifetime. So that for me, that's actually the most persuasive argument, that it's that dark matter is out there and it's not made of atoms. Everything else, this could be atoms. I don't know, the right kind of gas or dust or maybe bowling balls or something. Same with this. This is like, the universe could be full of like, I don't know, like bowling balls, right? And they wouldn't, they have a really small cross section. They wouldn't interact with each other. They would gravitate. They'd be super distributed. And so you could these things you can make with normal matter. This you can't make with anything made out of atoms. And so that's what's really persuasive to me, to say, great, this is a sign of stuff beyond the standard model, because there's nothing, no particle movement accelerator fits this. Right? Did that make that get the story? Right. Okay, and then here's the just jumping away from dark matter to say, okay, fine, there's this other stuff out there. Let's talk about the QCD Axion, and now you have to start from a whole new story. And you start with something called the strong CP problem, and that is, I mean, this is you probably cringe when someone draws a nucleus and they draw the little quarks like they're things. No, they're like their heels, like they're whole. It's anyway. But still, I mean, from our simple picture, you'd seem like, all right, these things are unbalanced, and you'd have to lay them all exactly on top of each other to get no electric dipole moment, right? Like this, the way it's drawn here is there's an electric dipole moment in this direction. There's more plus in this and more minus on this side. And in fact, but up and down quarks are fundamentally different. And so even if you try and lay them on top of each other, the natural thing to find would be that there's an electric dipole moment in the neutron. More fundamentally, this has to do with whether or not the strong force is CP symmetric. That is to say, does the physics look the same if I take all of my plus charges and turn them to minus charges, and all of my axes I switch their direction? And oddly enough, this is the same as saying, does time look, does like all the collisions look exactly the same with time going forwards and backwards? And funnily enough, wait, where was I? Right. Funnily enough, you'd think that it's more CP asymmetric than it is, and yet when you go and measure the neutron electric dipole moment, you find that it is more than 10 orders of magnitude smaller than you would expect from standard QCD. I'm skipping over like the instant-on story here because I don't think I really understand it very well. I'm not sure if I can explain it to you very well. So this suggests there's something canceling out CP violation with strong force, and or there is something that has a symmetry that really forces these quarks to line up exactly on top of each other. And there are not actually a huge number of good ideas out there. One of the best explanation is a new symmetry called Peccei-Quinn symmetry, which as a whole side effect, well, I mean, it fixes everything, it explains the neutral electron. That part's fixed. And then, but there's a side effect is that anytime you introduce a new symmetry, you basically introduce a particle. And so this particle is called the Axion, and in typical, like typically if you have a theory, you've got a new particle that you don't really want, you make it like really light, you really weakly coupled, and no one's gonna ever find it, it's not anybody's problem. If it's not, that's not even true. For a very brief time, the Axion was like, oh, it's like a new pi naught, and if we look finely enough at our accelerators, we should see it at like masses that correspond to the weak force, because the weak force is super exciting and everything should be at the weak force scale. This is also the argument for the ellipse, I guess. Anyway, it wasn't there, and so it was thought, all right, we know the scaling, it's got to be light and weakly coupled. No one will ever worry about it, except if you look back in the early universe. You find that way back, like before this cosmic microwave background, possibly before inflation, temperatures are so high that this Peccei-Quinn symmetry is now no longer, or its symmetry is not being broken in a way that fixes CP symmetry, and so energy gets dumped into the Axion field. I guess the way to look at it is that if the Axion has no mass, and it's just like a field that can take any value, then it can take any value across the universe. And then once you hit a certain transition point, there's a preferred value. And all of a sudden the universe is like, it's like a plucked guitar string. And you put energy into the waves, and these waves become Axion particles as the universe expands. That's what's going on here, is something going from just like field excitations to know this acts like a particle across after the universe gets to a certain size, or maybe cools to a certain temperature. And so as the universe gets bigger, the density goes down. That's like non-relativistic matter. So this could be dark matter. Yeah.
This might be a naive question, but why does a symmetry result in a field?
So I guess if I were to formally say it would, so a symmetry in your Lagrangian or Hamiltonian, you can show that leads to a conserved quantity. And if we just think of the universe as just a whole bunch of collected, a whole bunch of collections of fields, and we have to go and start naming particles. Particles are things that last for some amount of time, and so they're conserved in some sort of, just to some degree. And so I guess that's I don't know, Vincenzo, is it that symmetry leads to conserved quantities? Particles are basically semi-conserved quantities.
Yeah, and also, but in this particular case, I think the fact that the continuous symmetry is broken leads to nearly zero mass particle. This is the Goldstone theorem. You can think of it so. When a symmetry is something you do to your physical object, and leaves the thing in change. Turns out that there are some symmetries of the equations of motion that are not symmetries of their solutions, or the ground state solution. And when this happens, we have many ground states, right? And as you move around those ground states, there are collective modes that are zero mass, zero gap, right? And those are those particles. So I guess I would refer to whenever you break a symmetry, you get a new particle.
Okay, when you break a symmetry.
When you break a symmetry, you get a new particle with zero mass, when you break technically a continuous symmetry. And you can think of the zero mass particle as the particle as you move around the valley of minima those are your new particles, new excitations. It turns out the axion is one of these. And the symmetry is also broken in such a way that you also give it a small mass. It's not exactly massless, but right. So this is one way of thinking about it. This goes from and by there are many, every broken symmetry has its own part. For example, ions are very light, almost massless compared to protons, and the other particles associated to another broken symmetry, kind of. So I don't know if this.
Here's a question: is just that so when you introduce Peccei-Quinn symmetry, the Peccei-Quinn theory, do you add any degrees of freedom?
Oh, a bunch of degrees of freedom.
Okay,
so put them so high that you don't.
Right. Okay. Okay. So maybe fundamentally is that when you add more degrees of freedom, you have the chance to make more particles.
Of course, yeah.
So
to make more symmetry.
Yeah.
Break them.
Yeah. Okay.
It's a. Yeah.
So maybe the fundamental thing is that you're allowed to add as many extra degrees of freedom that no one can see up at high energies. And then you break symmetries, and that's how you get low mass.
And then you get a low mass.
Yeah. Okay. Yeah, there we go.
Yeah.
We're on the same. Right. Anyway, so there's this Axion dark matter creation myth that says, gee, if this Axion's out there, we expect to see a lot of matter in the universe that's made in Axions, and they're too weakly coupled to turn into anything else, and so it's just out there, gravitating. And if you knew your story really well, then you would say, great, I know there's this much dark matter in the universe today. I measure it from velocity dispersion of stars or whatever. Or maybe this is cosmic microwave background actually the right way. And you say, great, so if I go back and I have this story about how when this symmetry is broken, I get these new particles and energy is dumped into them. The temperature of the universe at the time that I break this symmetry should tell me how much dark matter I have today. And so working backwards, if I take the amount of dark matter I have today, that should predict the energy scale, the symmetry breaking, and thus the mass of the particle, and that tells me how to look for it. It is not that simple. Or I guess it's rather the story sounds simple, but if you go and say, okay, great, I'm going to take the last 10 years of papers of theirs who've tried to do this, then I'll show you those actually in a second. Then or at least for an experimentalist, you're like, you were making a measurement with very large error bars, and so you just kind of draw error bars and say, okay, here's a mass, here's my scale of possible masses for a particle. Notice it's up nearly optical, okay, this is milli eV, all the way down to just impossibly tiny. And the idea is that if we just don't know how inflation works, and so if this phase transition is broken before inflation, really any of these masses, no one would be surprised if that made up the amount of dark matter we have today. If the symmetry is broken after inflation, we understand things a little bit better, but there's perhaps 3 orders of magnitude uncertainty in that. And so for an experimentalist, that says, okay, you're looking for a particle, the mass range could be wide. This has become, I don't need to impress you, but it's more popular. This is for like other talks where I'm trying to convince funders that like the community is interested in axions, but this shows how like papers of axions have been growing and growing. And I flatter myself to think in part this is because of the experimental work has finally gotten to where we can actually look for it. Where back in 2007, this is when I was just joining, we were not looking at the most theoretically well-motivated axion spaces. We were working on getting the detector better. And then somewhere around here is where the detector got well enough to hit like really theoretically motivated spaces.
So what happened in 2016?
So I flat stole this plot from this guy.
Okay.
And I've never asked him what I should do. Yeah, there's papers you can read if you want to see what's the status among the community. You don't care about that. There's a prize to one of the Professor Rosenberg is the professor who brought the experiment here. I'm showing it off. I guess it's been a year to take that slide out. But since I met you that introduction, you should mention that the Panofsky Prize went to so Leslie Rosenberg with David Tanner, who's at the University of Florida, still in our collaboration. Leslie still comes to lab. So right, there was this whole thing. This is like my standard, like I go out and like to some other university and give this talk, and I have to convince people that my research is important. You may be familiar with this being a challenge. And so part of it is it's not only it doesn't have to be important, it has to be. Anyway, looking for detecting axions. All right, undergraduates may or may not know what a Lagrangian is, but you may be comfortable with the idea of a Hamiltonian. If not a Hamiltonian, at least a measure of energy of the system. And so if you're writing a whole bunch of ways to contribute energy to the system, and what we call a particle interaction is just saying, look, if this particle and this particle and this particle are all in the same place at the same time, that there's extra energy in that. And so here, this is if there's an axion and a photon and another photon all in the same place at the same time, then by however much this value is, there's extra energy in the system. And that is to say, fundamentally, an excitation in the axion field can turn into an excitation in 2 electromagnetic fields. So you can make 2 photons from an axion. Equivalently, you can do the same thing with gluons and nucleon spins and axial nuclear backbending modes, and even electrons. Perhaps this coupling isn't particularly well defined, but it could be there. But fundamentally, we understand electromagnetism really well, probably better than we understand anything over here. Furthermore, if these axions are super light mass, like sub-eV, none of the objects here are sub-eV in mass. And so you're only going to kind of bounce off them. Well, here you can actually make photons. And so this is the exciting coupling. Here's axion turns into 2 photons. And so we make plots like this. Right, here's where this is the thing that I hate where people do, like you leave a laser pointer on, you've got a plot, you're following that. What is going on? This is terrible, right? Okay, so this is when you show a plot, you say, I have a plot here. You define the axes. I've just talked about this axion photon coupling. It is on the y-axis there. I've talked about the axion mass. It is on the x-axis here. There are many orders of magnitude covered, and there's a relationship between these two. This yellow band here, this theoretically motivated space, that in this region it makes sense that you could have an axion that solves the strong CD problems, QCD axion as we call it. There's white space here. You might find a particle there, but it probably wouldn't be the QCD axion. There's a whole lot of fancy colored things here. These are all experiments or astrophysical measurements that have excluded particles from being with these parameters. And there's a slight blending here. Notice there's this row. This is talking about dark matter density. Not all of these truly assume the axion is dark matter. If you want any one of them, I can tell you which it does, which doesn't. But the one that I do, ADMX, which these are collectively known as axion haloscopes, do assume the axion is dark matter. And to make a measurement of the measurement is made of dark matter density. Because if there's no dark matter at Earth, we're out of luck, right? We know nothing about the particle physics. And if there's no axion photon coupling, we're also out of luck. We measure the product of the two. Anyway, the whole point is to convince you that there's many interesting measurements to make, but the most interesting are the ones I'm going to tell you about because they're reaching into this exciting yellow band. And furthermore, I try to convince you that this mass range is also a pretty exciting mass range to look for axions. You also, I might slip out and say the words KSVZ and DFSZ. These are very specific benchmark models that tell you exactly what the axion photon coupling is. They're not necessarily true, but they're used by experimentalists to say, is my experiment is my experiment likely to make a discovery or not? And so if you're on the lower one, then you feel you're likely to make a discovery because you're exploring many possible ones. So if you're on the upper one, you're maybe less likely to make a discovery because you're not probing all sensible ones. I said there were other couplings. There are other plots you could make for these couplings. They are much less, they're probed much less well here. So this is Professor Barry Akhtar at UW realized that axions would make black holes spin down. It's super cool. But not the topic of this talk, so I should probably go on. All right, here's the story where if you zoom in and say, all right, I'm just going to go through the archive, and I'm just going to, every time somebody predicts an axion mass, I'm going to write the axion mass down and put it in a little bar here. And so here is axion mass, and each one of these is a paper with somebody's model. And this is what I mean when I say there's kind of confusion and disagreement about exactly where to look. And so when one's building an experiment, one just kind of says, all right, somewhere in there is where I go. And there's further complications. There's interesting things like Star Trek sounding words like cosmic string decay is a source of axions, but it's probably beyond what we should talk about here. Okay, so that justifies zooming into this micro-eV to milli-eV mass range. So once again, axion photon coupling versus mass. These are the axion haloscopes. This used to be a much barer space when I started this a decade ago. I'm going to be telling you mostly about ADMX, but there's other people out there. There's a lot of like smaller experiments that prove you could do an experiment and almost reach these. But what you really want to do is just exhaustively search this whole region here. That's what we're working on. It's kind of fun to talk about the sensible length scales versus mass, because you can think about the de Broglie wavelength, the Compton wavelength. This is the difference between like the matter wavelength and like if I make my particle into a photon, I would say it's wavelength. And so, and the axions are non-relativistic, so the wavelengths end up really long. And so we find that around the masses we're looking at, the axion's matter wavelength is large compared to your laboratory. The photon wavelength is about the size of your laboratory. And the correlation time has to do with if I measure the axion field, like is over what length of time does it appear like it's truly a sine wave? And at what length of time is it just like more thermal? And that's pretty long. Well, I mean, if you put it in seconds, it's like milliseconds, which is pretty long for modern RF electronics, but not very long for you. So you can't, if this was up at like 10 to the 9th seconds, then you could use it as a time beam, just make a discovery and use it as a global time standard. You're not going to do that with this. Anyway, that tells you you're going to be building structures that are kind of laboratory scale, and you can assume that the axion itself is just this constant field across your experiment. And it's really quite nice in that if you go and look at the number density of these axions, they are so high, and you go dig around in quantum mechanics and you find that you just treat them classically. There's just like the whole thing is so dense that it's like if you're saying, oh, I'm looking at a cell phone signal, do I need to worry about each photon? No, the photons are so dense in space, I can use my classical ENM. And so because you can make the axion field completely classical, that means you can tie it to ENM. And so you can take Maxwell's equations here, add a couple terms, And now you have a model of both electromagnetism and an axion field. And furthermore, the axion dark matter is really dense and it's non-relativistic. And so this where you see an A, it just turns into like a sine omega t. And so from there, you go and do kind of junior level like antenna radiation stuff, maybe senior level antenna radiation stuff. And you can figure out, okay, if I have an axion in the presence of a magnetic field, it's living on the same side of the equation as a current. So this looks like an antenna. These grad A's, by the way, just make them 0. They're pretty small. Instead of the wavelength's really long, so it's small. So this is the one you care about. So if I have a magnetic field anywhere there's dark matter, it's like there's a small current radiating at whatever the axion frequency is. So you just have to pick up that radiation. And then here's the demo I do in class where you do resonant transfer. That's to say, if I have 2 tuning forks and they're tuned exactly the same frequency and they only communicate by sound, you can still whack this one and transfer energy very easily over to this one. But if they're detuned and you whack this one will not get a very high amplitude. And so you find that you can get good energy transfer even with weak coupling between 2 resonators if they're tuned to the same frequency and the equations of motion are the same as the axion and electromagnetic cavity resonance. And so that's why we build electromagnetic cavities, is to get good power transfer from dark matter to our experiment. Practically speaking, or rather cartoonly speaking, is so you have this axion wave, you have the magnetic field. Ignore this virtual photon thing. That's for people who are really hardcore particles. You can't think about fields anymore. So that's just the magnetic field. So this is like a current. The current emits a photon. The photon bounces around. It's amplified, digitized, and then if you look at power versus frequency, whatever the right frequency for the axion, HM of the axion, H omega equals mc squared, you get a bump there of excess power of dark matter turning into power. We didn't know the frequency, and so we have to draw this tuning rod because that tuning rod moves around here and it makes the standing waves in this cavity change frequency. And so you want that frequency to tune to your axion frequency. Where did I go? Oh, this is the part where no, okay, if you this is what, for older people, I say it works just like an AM radio, but I think at this point no one has AM radios anymore, right? That's like really old technology. But it turns out like this stuff, like we pay tens of thousands of dollars for these electronics, but fundamentally it's like if you draw the layout, it looks like an old-fashioned radio. Because you're getting some high frequency signal, mixing it down. Okay, so to build one of these experiments, if axion dark matter turned into photons a lot, we would know already. So the signal is going to be pretty small. Signal is proportional to the cavity volume, the magnetic field squared, resonant volume of the cavity. You want all those big. And the noise is proportional to basically the temperature, right? The thing is black body radiation and the amplifier noise. And so you buy the best amplifiers you possibly can, and then you cool it down as low as you can, which turns out to be pretty low. Like for us, it's 80 millikelvin today. There's a picture across from the dorms of a collaboration meeting. This is 2023. We've had one since then, but I don't think the picture was good, so I haven't changed it out. So that is at Fermilab, but it's in front of like some big Fermilab piece of equipment thing that has nothing to do with vaccines. Anyway, this actually counts as a pretty small collaboration. Maybe we're up to mid-sized, but it's for particle physics. They usually get much bigger than this, but it's not quite just a benchtop experiment. So to move from cartoon to machine drawing to photograph, there's the cavity where there's standing waves in here and the axions come in there. There's the magnet, it's about 8 Tesla. We never get it quite to 8 Tesla. Amplifiers go there. We'll talk about them a little bit. And this is all this cryogenics. I said, so you can see it starts at 300 Kelvin room temperature, and then it's down to 40 Kelvin by that plate. Now it's 4 Kelvin because there's a bunch of liquid helium here. And you pump on the liquid helium, you get down to 1 Kelvin, and then you use this helium-3 fusion refrigerator, and that takes you down to millikelvin. When we made this slide, we can only get down to 100, and we've got down to 80 now, which is, it was a lot of work. So moving into that resonator. This is what it looks like if you take the lid off the cavity. This is last year's cavity. We've got these 2 rods. They're kind of the size of baseball bats to give you a sense. They move around in a little circle, and if they're close to the center, it's like a coaxial resonator. If it's close to the edge, it's like an empty cavity. And so you get lower frequencies and higher frequencies. And you can plot these out if you map. So you take frequency versus rod position. And so this is sort of 360 degrees. And you try and shove power through the cavity. And if you're shoving the power through on, and let's just say like I have like an oscillator, I plug in one end and I have a listener on the other side and I measure out the other side. And so it's a cavity filter. And so if you're on resonance, the power goes through, and you're off resonance, the power doesn't go through, and you make the color how much power there is. And so these lines are actually resonances. So any particular position, there's a resonance at what, that's 620, no, I can't read with this angle. Anyway, resonance here, 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 but as I move the rods to the center, the resonant frequency goes up. And then you have to do some calculations since you've already got you've got your Maxwell's equations, you find your wave equation, you figure out which of these cavity resonances interact well with the axion, and it's the lower. The rest don't do it very much.
Can I ask a question?
Yeah, please.
This is measured, right?
This is absolutely measured.
Measured, and I'm curious about the modeling capability. In principle, you could predict. So you have the Maxwell equation, you have your system. You can
Yes.
How well does you don't trust modeling, or are there too many uncertainties?
So there's all sorts of things that can go wrong. So if this gets tilted, right? Like you've machined it to be straight up and down. If it's tilted, it shifts these up and down a little bit. In the modeling, there's big length scales, like the length between the rods, and there's small length scales, like the length between the top of this rod and the top of the cavity. And that's an interesting challenge for modeling software. I mean, fundamentally, you model this and you get it to, I don't know, 0.01% or something. Now, that being said, you're measuring gigahertz and you're measuring things at the hertz sensitivity. And so you can measure 10 to the 9 or better. And you can actually do 10 to the 10, 10 to the 12 if we want. So yes, you can model it, you can measure it better. And so what you do is you model it and you measure it. And as long as they pretty much agree, you think you're solid. If you model it and then you measure this and you get something off, then you're suspicious because your model tells you your overlap between the axion wave function and the photon wave function. And if your model's not predicting the frequency you measure, you might be wrong with that, and you need to go in. That becomes an uncertainty to determine your coupling. But yeah, when we have the group in Australia does a great job modeling this. There's other things. It shifts. So you have to read this out. So that you put an antenna in, which is just a piece of wire. It's like somewhere there. So it's not pictured here. And that perturbs the fields a little bit. So you can decide whether you model that antenna, and you can move during operations either intentionally or unintentionally. So yes, we do model it, but you can always measure it. Okay, here is the thing that you're looking for. You're looking for in a power spectrum, so frequency in the x-axis, something in the y-axis that has to do with power. Here, where we use the word SNR about signal to noise ratio, because a lot of times this power is going through a lot, or the waves going through the system are going through a bunch of cables and a bunch of amplifiers and a bunch of components. And so what we're really interested in is the relative height between this piece of potential signal and this noise in the background, which is thermal noise. And so all of our calibrations, all of our questions, all of our ability to say what signals can we see or not see is our ability to correctly predict this thermal noise and say, tie that to a power. Fortunately, people who study thermodynamics, it's Johnson noise, it's a black body radiation. It's very well understood. You can calibrate it by. There's a lot going on here. So this is the cavity with the axions. You don't have to look at that. You can instead look at this hot load, this heat load that goes through this complicated mess here. And you change the temperature of this and measure the total power way out somewhere else. And it's exactly linear, just as you expect. And the intercept of this line tells you how much extra noise is added by all of the mess here. And that is your calibration. So your calibration is, someone at NIST makes a temperature sensor. Crust, you put that temperature sensor there, and then by heating it up and cooling it down, you can tell what power you're sensitive to. Maybe we won't get into this other than to say that we use these superconducting amplifiers, the same things they use to read out qubits, they're kind of cutting edge and a huge headache to work with, but they're required because they're the best amplifiers in town. They're down to the point where you're limited by quantum mechanics. You get extra noise from your amplifier based on. If that's exciting, I can talk a lot more about it. Are you that exciting? Yeah? No? Okay. All right, so it's exciting to you? I'll talk about it. Okay, all right. Okay. So if you're measuring a field, the amplitude of the field and the phase of the field do not commute as quantum measurements. I wanted to say they're quantum conjugate things, but they're not. They just don't commute. But this means that there's a Heisenberg uncertainty between the two. And so if you think of a regular linear amplifier, you put in a sine wave and you get out a bigger sine wave. And so so to get a bit, if you're trying to build this bigger sine wave, you both need to know the original amplitude and you multiply it by gain, and you know the original phase, and you put that phase into the thing you got out. You're measuring both things at once. So turns out you cannot do a perfect amplifier with no noise in this case. And so that adds a certain amount of noise, and it's basically a half photon's worth of uncertainty. And so that is capable, that's what's doable by these, she's plugging one in, right? It's like it's in there, one of these Josephson parametric amplifiers. They're not quite operating them at those noise levels, but if you want the lowest noise amplifiers you can make, that's what you use. There's a whole quantum optics argument that's more elegant about it, but I like it. It's like basic quantum mechanics. You're like, these two things don't commute. You're measuring them both. Yeah.
I'm going to ask a silly theoretical question. So if you had to treat, which one is more important to you, amplitude or phase? I would guess phase, timing, frequency, but I don't know.
No, because if someone came, wrote a paper, I discovered the phase of dark matter, you wouldn't care. No one knows. Like,
but the
you care about power. You care about like there are actual particles, like number of particles.
Isn't that the mass, the phase? I think in my head is phase is frequency, so the mass.
No, but you can the frequency is a different matter.
Okay.
This is like, the phase of a particular wave is not what you want to know. You want to know that there's a signal or there isn't a signal.
Okay. So
right, and so amplitude is the only thing that matters. And if I'm going super slow, I might not get to it, but I can talk to the end about what we call post-quantum limited amplifiers, or quantum sensing. Everyone's applying to this quantized 2.0, which you can make an argument that linear amplifiers eventually become inappropriate. What you want is a phototube.
But then can you explain the significance of the phase in this context? So phase is nothing, so it's not frequency. Okay, good. Thank you for. Why do you care about the phase?
You don't care about the phase. That's the point. That's it. So correlation time. This is my phase correlate. How between what time scales my phase correlated? It's like milliseconds because the dark matter is thermal. So the phase is a complete. It's not even constant. If it was constant for like years and years and years, then you'd say, okay, that's something I can measure. But it's like, what's the phase of photons coming from the sun? Well, it's all over the place. It's thermal. It's not like it doesn't contain any information. So yeah, so fundamentally you realize that you're intentionally measuring something that's useless. And that's in quantum mechanics eventually makes you pay the price for that. Anyway, right, okay, so you've got these fancy amplifiers, and this is what it looks like if you pile your data up. Each of these is maybe 100 seconds. So this is 20 minutes of data. And you make a power spectrum, move the rods, make a power spectrum, move the rods. You can't see the cavity resonance in this particular plot because everything's been flat. But you can see a synthetic signal. So this is where you inject with an antenna something that looks like an axion. And indeed, as you tune your system so that it's on resonance, which is the center of this band, it becomes a big bump. And as you tune it away, it becomes a small bump. And so you add these together in a statistically sensible way, knowing that it's enhanced by the cavity resonance in the middle, and this is where you get this plot there. And so that's what the process is. You imagine these just 100-second cycles. So make a power spectrum with the rods, test stuff. Make a power spectrum with the rods, test stuff. And at the end of the week or the end of the day, you go and check and see if there's any bumps. You can go back and look for them. And there are always bumps. For one, there's statistical fluctuations, right? You're scanning as fast as you can, and so you're at the level of the statistical sensitivity. There are sometimes radio frequencies leak in. This is at cell phone frequencies, this is at Wi-Fi frequencies. If you don't have everything sealed up nicely, one cable can carry in something that makes a mess of your data, or usually it's just one line. There's also, we pay collaborators to intentionally put in synthetic Axion signals. So at any given time, people, I feel like there's like, I heard there was this rumor about like, oh, maybe ADX saw something, and I'm telling you, you can't deny the rumor because we are actively taking data right now. There's always, about one synthetic signal per megahertz. There's always something that looks like an Axion to keep us on toes. So you don't know for sure we haven't until the analyzers have completed and we write the paper. So anyway, because that's to keep us on our toes and do all these checks to say, okay, so there's a bump, great, go back and rescan that. Is the bump still there? If it's not there, it's probably not dark matter because we're looking for dark matter that's uniformly distributed in our solar system and it should always be there. Turn off the synthetic Axion injections. So okay, call them up, call up our team of PNL and say, okay, turn off the injections because we see a bump. And most of the time they have to do that. They're allowed, by the way, to not turn one off to get us to test the whole detection exercise. Anyway, so you check that it's persisted after they turn that off. You then check if it's radio frequency interference, and you can do that by saying, is there a signal outside the cavity, outside the magnetic field? It's also this. This is the point, by the way, that where we say, okay, we're going to do this huge operation where we ramp the magnet down because the signal strength should go as a magnetic field squared, and that's not much interference can possibly do that. However, it's kind of a big deal. So this is where we say, okay, we've done all the checks and now we've got to ramp the magnet down. And we've never actually gotten that far. We've never gotten to a point where it's like the signal is so good that we're going to ramp them. We've gotten here where there was like serious, like everyone was like, oh, really excited, but it turned out to be a synthetic signal that the red team were paying to do this tricking us. And actually it turns into this game between the analyzers and the injectors because and here's the synthetic one that got us really excited is here's some just example plots that the analyzers were making to do these checks. This is saying, does it follow the cavity resonance? Because frequently we'll get a signal and you make this plot and it's flat, and that says, so this is power that you're measuring versus frequency offset from cavity resonance. If it's flat, that's saying the signal is coming from outside the cavity. That's not dark matter. This one's coming from inside the cavity. This was a measure of width. I don't know if I can even describe this super well, but this is like what's the simple way of saying this? This is so the width of the signal has to do with the kinematics of dark matter. And so this is not particularly useful in saying, is it or isn't it dark matter? I guess if it was like way wider than this, then we would say that's not very likely dark matter. But this is an interesting measure where the injectors made it slightly colder than you would expect regular dark matter. But that wasn't used to decide whether it is or isn't. This one was kind of fun. So this is where the postdocs decided to get clever. And they go and say, hey, remember how there's multiple modes in the cavity and we know only some of those modes couple with the Axion. Let's go tune a different mode to the same frequency and see if we still see the Axion frequency. The injection team wasn't paying attention to what modes on there. So they see in both the mode that you would expect to see an Axion signal something, and the mode where you would not expect to see an Axion something. And so this is where the analysts called them up and were like, caught you. This is not the real deal. Like, all right, busted, you got us. So we didn't start writing the paper or ramp the magnet down or anything. But it's a fun story, and it also shows we're very serious about planning to make a discovery, and so we have this whole system to say yes or no, is this the real thing? Right. Given we've not seen the real thing so far, what we can do is exclude parameter space. We can exclude Axion couplings and dark matter densities as a function of Axion mass or frequency. So this colored region is various years, 2018, 2019, up until recently. Excluded region. So this is where there's not Axions. This is assuming some dark matter density. You could also say, look, we really like this KSVZ benchmark model. If that's the real Axion, But there's, you know, some dark matter is axions, some's WIMPs, some's maybe little black holes or something. What fraction is axions? And so you can say, what is the dark matter density, assuming the KSP model for these masses? And you can see that for these masses, we are down 10-20% of dark matter could be axions at the most at these masses. So if you know, we never, it's never a final exclusion thing. You never say there's no dark matter that is axions. You could just say most of it isn't. Like, who knows? There could be a very low density, but then this begs the question. There's got to be some other dark. Okay, oh, I'm running low on time by now, I think. You can do high resolution searches because this, so if you're looking at this power versus frequency with the noise, this width tells you about what is the temperature of dark matter. That is to say that, you know, if you were thinking about dark matter as particles, they all have some sort of velocity and they're all going different directions, right? It's thermal, and if it's cold, the signal becomes very narrow, and if it's hot, then it's wide. It can't be too hot, because if KT gives them a velocity that falls out of the galaxy, then galaxies don't stick together. So you know there's like a maximum temperature. But there are interesting ideas out there tied to the axion creation myth, where you instead have extremely cold flows of axions. And so you have narrow peaks, maybe several narrow peaks instead of one wide one, and you can search for those. It's kind of a specialist thing, but it's a great thing for a graduate student to get their arms around. Like, I totally got this model. Okay, let's see, this is up to April. So this is just saying, look, we're now looking at a new frequency range here in April. It's you know, there's calibration, like you can't always be sure about the calibration, so we don't know if we're actually past this DFSC limit. I don't think we are. I think we're not excluding DFSC over the whole range. That's based off exactly how the amplifier calibration. So we'll probably have to make another pass. If you squint here, it's actually it's an exciting time. So it used to be this stuff, ADMX was the only game in town. We just scan Axion space as we felt like, and we'll make everything just right. There's a Korean group that has recently got Axion sensitivity competitive with us. I don't know if you can see it there. We made it it's really light in this spot. But they're eating up space above our last limits, and so we leapfrogged them, and now we're looking up here. And so now it's actually a race, right? Every day you're not taking data is the day the other person could discover the axion. Fortunately, there doesn't seem to be like, oh, there's plenty of space for everybody so far. But yeah, there's a lot of competition in like how fast are you scanning, right? Because if you don't know where it is, then the number of megahertz per day you can scan is your detection probability proportional to that. If somebody is 3 times someone else's, the agencies get mad. Or at least I use that to be like, hey, US Department of Energy, you want this dark matter to be discovered by the US, right? Well, look, the other people are scanning 3 times as fast because they've got money for these superconducting cavities. And if you don't fund us to the superconducting cavities right now, they're going to beat us and shame us. Are you going to stand for that? I don't know. I didn't give us the money yet. It was worth a try, right? Because I don't know. It's better than like building airplanes or just tanks or stuff, right? It's going to compete on some level. Anyway, and then I'll call up the people in Korea and be like, okay, I said this, you say this to get them to give you more money. Like we can try and it's so far it's nice and collegial. We'll see if it's staying. All right, future plans. Both us and them are planning on going up in masses. That's rough. It's slightly more theoretically favored than going down in masses. And so we have to build bigger and better things. As you go up in frequency, right? So there's something called ADMX EFR that I would advertise here. Maybe some of you will work on it as graduate students. The idea is that as you go up in frequency, the wavelength of the photons gets smaller, so your natural resonator size gets smaller, which means there's less dark matter, which means less signal. We're already operating at the edge of signal noise, so our scan speed would drop dramatically. As we go up in frequency, the only solution is, well, there's lots of ways to beat it. Lower noise, bigger magnet, stronger magnet, and with a bigger magnet, get multiple resonators and combine them. That's it's looking at here. So we've obtained this big MRI magnet here that's a little bit higher field and a little bit bigger volume. We're going to pack it full of these little resonators that operate at higher frequencies. That was a whole separate fridge for us to test out these ultra low noise amplifiers. And so my whole wish list for up to 10 gigahertz is New fancier resonators, higher Q, probably because they're superconducting. There's funny stories about that. Subquantum limited detectors, we'll talk about that. But large, that's just money. We've got one, not the biggest you could imagine, but it's the price was right, let's say. And then probably dedicated facility. This might just be that I'm getting sick of getting like called in weekend nights because the water chiller failed. But at the same time, like having it at an actual lab with a bunch of dedicated engineers, and eventually, I guess everybody's experiment grows to the point where you no longer fit in your basement, which is kind of sad. And also larger collaborations is kind of sad because it means just to give, I got 5 minutes. We'll talk about some of the advancements here. So I showed you just the big tin can or copper can resonator. You can imagine as you get smaller, you could make them smaller and pack them together. It's a hassle because they have moving parts, and more and smaller moving parts means things are broken more often unless you're very, very carefully engineering. But we're going to try and do it. We're going to make a Swiss watch out of this thing. So there it is with 4 cavities, and there it is with is that 17 or the 11? I forget. Anyway, each of these has their own separate motor. They all tune together. What a hassle, right? But then you have to combine them all and combine all the signals together in phase. There are other ideas out there for resonators instead of just making multiple cavities. You have this one, I don't know if you can see, but there's a copper divider in this that basically gives it twice the frequency that it otherwise ought to. There are people working on these things where you put a whole bunch of copper in here. They end up being super lossy. I don't know if this is the right. On the other end of the hall, I've got a setup where we have more like Fabry-Perot type resonators that you end up having to put dielectrics in. I had a graduate student who built one of these from scratch. It was amazing. And there's ideas. This is where you get like into the heavy duty modeling convention. So is that someone is like, oh, I think I can do it like this, and you're like, yeah, you got to prove to me in the model that this thing actually resonates and the field is the right way that matches the Axion. They're working. This is just results from these prototypes. Here's an interesting story, is that for a decade, I would stand up and I would talk about, oh, these high Q resonators and you want a higher Q. And I've got this copper cavity, and someone would raise their hand. They would say, oh, well, so wouldn't a superconducting resonator be a higher Q? Because that's what we do in the accelerator technology. And I would say, my best academic derisive laugh, you fool, it's an 8 Tesla magnet. If you put a superconductor in an 8 Tesla magnet, it's not a superconductor anymore. And indeed, that's sort of how it seems, right? Is that there's a TC and the high superconducting at higher frequencies is worse than superconducting at just like regular DC, because as soon as you've got a pinned magnetic flux that you can wiggle with an electromagnetic field, that's a new loss term, and it sort of becomes more lossy than if you just left it alone, left copper. So anyway, after a decade of saying that, someone has proved me wrong. Or rather, a number of groups have started doing this, and it's not all the way there yet, because you basically need the walls of your cavity. These thin film superconductors are basically parallel to your magnetic field, so it's more or less sneaks in between magnetic field lines. So they never go through. And there are groups that have done it. There's Fermilab, and you get these long lozenge-shaped things. The Korean group is like way ahead on these. They're using these high TC superconducting films that they've more or less glued on with some proprietary glue and have like a factor of 100 better Qs with cavities. They're not obviously tunable though, without ruining the whole thing. There's a graduate student at UW putting a tuning rod to say that we're testing these out too. Anyway, this is kind of a hot new thing. Is that if these work, then it's a game changer. But if you can make the cavities but you can't tune them, it's not actually useful experiment. Oh, yeah, okay, there's the zoom in on that. There's other ideas out there for going even higher frequencies. I don't think I have time to talk about these weird like antenna type things, but I don't know, it's the same electromagnetism, but they use different words because for some reason, just the way it was developed, like every couple orders of magnitude in frequency, you have to change all of your language for engineering. I don't know, I didn't make it up. Here's the thing that I was talking about, these quantum limited amplifiers. This is another way of getting better, is just, hey, we're stuck with this staring quantum limit, and I tried to convince you that it was a Heisenberg uncertainty principle issue, and that you're measuring phase and amplitude. You can squeeze it, which is to basically say, I'm going to dump all of my noise into my phase measurement and out of my amplitude measurement, and I will get better than, there's still Heisenberg uncertainty principle holds, but I've shoved all the uncertainty into the thing I don't care about. That's called squeezing. It's been demonstrated at Yale back in 2003. So another one of these things that if you get me going, I can tell you why I don't think it's actually going to work in the long run, but I don't think they've got a factor to it. This thing seems a little bit more exciting, also more complicated. If you have a qubit style thing, a qubit, it's either 1 or 0. And if you make it 1 or 0 based on whether or not there is or is not a photon bouncing around in the cavity, that has no phase information in it. So it's that's another way you're measuring the right thing, and that can have no noise, at least from that aspect. And there's a group at Chicago that demonstrated to some degree this. There's a whole lot of this is very technologically challenging because it has another one of these things is everyone uses these superconducting translon qubits, which don't work in magnetic fields, and the whole cavities in magnetic fields that are separated, you can photon from one place to another. That's all it is. That's more than just one graduate thesis project on that. But it's a promising direction. This is a magnet argument thing. You don't need to hear my magnet arguments. You do need to hear about the consequences of the discovery. So let's say we found it. Does anyone care except specifically people doing dark matter? Well, we went through this exercise trying to convince other particle physicists that it would be of interest to them. So for one, the process of making Axion dark matter happens at the cusp of inflation, either before or after. And so just knowing what that is probing physics that's going on far before anything, any other astrophysical measurement. Which of these models you pick, all of these models have skeletons in their closets. And that by that I mean so KSVZ, you expect 4th generation quarks. DFSC, you expect a 2nd Higgs. This can get very exciting for accelerator people. They're less excited when you say the 2nd Higgs is probably so massive you'll never see it, but you never know. General astrophysics, you get a lot of galactic information from the line shape. Is dark matter just like truly a thermal isothermal halo, or is it coming in flows? Are these flows from the very beginning of the universe, or are they because when two galaxies, like when one galaxy eats another, it sucks the dark matter in? That would make an interesting deviation from the normal line shape. And then finally, this is experimentally is an observation not be in this coupling would not be the end, is because you don't actually know which of these models is going on with just this measurement. You need to know what the electron and nucleon couplings are. Those experiments are very hard, but they're a whole lot easier once you know exactly the mass you're looking for. And so this would lead the way to a whole set new field of study. Okay, I think. Well, okay, there's and then you can imagine repurposing Axion heloscopes to look for gravity waves. I've gotten a little less excited about this. I had some undergraduates looking into this for a quarter or two. There are interesting things that make gigahertz gravitational waves, but there's probably none close enough that we can see them, let's say. I don't know. It's when you feel, do you ever like lie in bed at night worrying that you're going to be eaten by a small primordial black hole? Like it's just going to go through the earth and just wipe things out? Because if you're worried about that, I have an experiment for an early warning system for you. However, I think that fear is somewhat incompatible with our understanding of dark matter and black holes right now. But only a little bit. Anyway, I'll finish up by saying, all right, well, so I still think this is exciting. I've been doing it for a while, but that's because we transitioned from like instrument development to, okay, we're actually searching, we're actually hoping to make a discovery. We've got a series of experiments that get bigger and better with better chance of discovery in the future. There's a lot of study and pulling in from hot things like quantum computing to improve the Axion heloscopes. And we are scaling it up to hopefully we'll make this discovery a reality. Is you can rule out all the interesting parameter space too. I try not to dwell on. Okay, thank you very much.
What makes you like believe more in Axion dark matter as opposed to like WIMPs or something?
So I find it very persuasive. In the very beginning, so we need something to be dark matter. And then I had the story about the neutron electric dipole moment and this strong CP problem. There's no real good other option for the strong CP problem. Maybe you know better options than that. So you can make the up mass 0, but that's basically excluded. Yeah, it's not gonna happen.
And it's not an option.
Well, I don't know, making things 0 seems nice. Anyway, so all right, so you're stuck with, all right, so there is this serious problem in nuclear physics. There is one good solution, which doesn't make it for sure the solution, but there's one good solution that naturally makes a bunch of stuff that's got to be dark matter. I find that like these people were not talking to each other when they came up with these things. And so I find that too good to be true in terms of coincidence. That doesn't stop it from being like, oh yeah, axions are dark matter, but they're only 5% and the rest is WIMPs. Then I'm out of luck. Yeah.
So let's say that they don't exist. How long would it take before you've excluded all of its parameters?
Well, as I said, given the experiments that we have now, we're looking for axion dark matter, and we can exclude and say, oh, like, you know, currently I'm saying, look, if it's made, if 20% or more of the dark matter is made of axions, then I'll see it. They could exist, but they only make 10%. There's enough uncertainty in the creation mechanism. So it's 10% axions, 50% WIMPs, 40% primordial black holes, let's say. We can't exclude that scenario. We could build, and so I'm like, so I could ask for 100 times more money and 10 times more time, and then we could exclude 10%, but that doesn't exclude 5%. So yeah, I have to be careful about saying, you know, I could talk about like you can make it like, all right, it's unlikely that axions would have this mass and still not be dark matter. And that the nice thing is that would like reopen this wound in nuclear physics of like the strong CP problem, which many people are just like, oh, it's solved. There's an axion. How long would it take? So to cover the good space for dark matter, that is a 10 or 20 year kind of problem. To cover all possible space is maybe outside the range of gravity. Though I don't know. There are people who, if I go back to this thing, there are people who are proposing experiments that look at this range, that swear they can take this experiment and scale it by 1, 2, 3, 4, 5, 6, 7, 8, 9 orders of magnitude. It's a tough game, but the argument's pretty persuasive. I mean, this is really small. This is 10 centimeters, right? Like, so there's 10 centimeters in like, you know, a found magnet in the dumpster. So there's a lot of room to improve this. So I want to. I don't want to be too down on them, but I can't tell you how long it's going to take to get those orders of magnitude. And then this lower bound, there are certainly people who want 10 to the minus 22 EV mass axions. For whatever reason they want it. I don't know, I wouldn't say it's motivated, but they for some reason like that. But there is a bottom. If the axion mass is so low that the de Broglie wavelength is bigger than the galaxy, it's probably not dark matter. Like literally can't fit it inside. So there is a bottom, but it's way down there and it's not obvious. This thing keeps going down and it becomes so weakly coupled. It's not clear how you get at it.
It's like, do you have any intuition as to where you think you'll find the axion?
Well, that's I don't know. Which of these people do you think sound credible? That's like literally what you're asking me is not only who, you know, who's credible here, but also which of these models is the main production of axions. And this is very suggestive here. So this is very suggestive in post-inflationary models, it's not worth looking much below micro. But I mean, nobody understands inflation. Not everyone believes inflation. So there's a lot of more freedom here. There's a whole argument about saying, look, even if it's happened before inflation, it's like you're like randomly rolling the dice. And you're picking an angle between 0 and 2 pi. And so here, with a mass here, it's like saying there's a region, there's a slice of the circle of pi over 2 that gives you a mass here. Down here, the slice is only a part in 10 to the 3. And so for a long time, I was like, okay, so you'll never find the Axion here, right? This is so unlikely. But then I talked to someone who studied inflation, and they convinced me that it's not obvious how to play, like how to do odds betting across inflation. Because if you have, if there's different, if things have picked this angle differently, and that affects how much they inflate, and inflation is like an exponential thing, and I'm trying to do some volume integral, like, all right, we live somewhere in space. And so there's an entire volume of space and different regions have picked different thetas. But they're changing size. Am I doing a volume integral? When do I do a volume integral? And so I became convinced that inflation messes up how you would do like Bayes rule backwards and infer likelihood. So that's why people still think this is reasonable. Also, they might say, you might make an argument that if conditions are such that all of the parts of the universe that picked numbers here were inhospitable to life, then we're sick, right? Of course we're in that. That's the entropy. I'm not sure I buy it in this particular case, but it is a valid thing to say. I can't tell online if there's, oh no, I guess I can. See.
Okay, any other questions? No?
It's just something in the chat.
It's been there for a while. All right, let's thank you very much.